The TCP/IP protocol is actually made up of something called TCP protocol and IP protocol. Actually, with a few more protocols in there. The TCP/IP protocol is multiple protocols all tied together into one thing that is called TCP/IP. The main protocols in here, though, in TCP/IP are TCP, which is Transmission Control Protocol, and IP, which is Internet Protocol. So what IP is IP is the protocol within TCP/IP that controls routing of information to different computers, different devices, and different servers on the network. So you will have heard of IP addresses. The IP protocol deals with these things called IP addresses, subnet masks, default gateway, DNS, etc. The IP protocol is what allows two computers to figure out where the other one is so that they can start communication. So IP is about routing the information. So it's how computers discover each other so that they can start communicating. Well, once the computers have found each other, then they do need to start communicating, and that is where TCP comes in, Transmission Control Protocol. Windowing is the process by which the client computer sends information to the server computer. So when two computers are trying to talk, windowing is the process of how that data is sent from the one computer to the other computer. IP connects two computers together. TCP is what then deals with the communication between the computers once they've started talking to each other. So let's talk about the components of a TCP/IP network. The first thing is what is called the IP address. So the IP address is something that you'll see, and you'll see it's like 10.1.10.1, let's say. That is an IP address. IP addresses are addresses that are used to signify every computer or device on a network. Every computer or device on a TCP/IP version 4 network needs an IP address, 10.1.10.1, 192.168.1.1, etc., 207.65.44.1. These are all IP addresses. So every device on the network needs what is called an IP address. So then, after you have the IP address, you have something called the subnet mask. Now in the next section we're going to talk a lot more about the subnet mask, so we're just gonna just kind of glaze over right here. The subnet mask is basically a way to segment a network logically so that different computers and different devices cannot necessarily talk to other computers and devices on the same physical network. The next thing after you deal with the subnet mask is something called the default gateway. The default gateway is the router for the subnetwork that you are on. So basically what the default gateway allows is your computer is going to look on the local network for the computer or device that it's looking for. Let's say it's looking for a website or it's looking for a server. It's going to look at the local network first. If it can't find that computer or device on the local network, it will then go to the default gateway and it will ask the default gateway to find that computer or device on whatever else is on the other side. So basically what happens is, you have your office here and you have the internet out here. You have your computer and you have your router. So what happens is your computer with its IP address is looking for a website. Now this may seem a little funny, but basically it's looking for a website. And what it will do is it will first look at all the computers in the internal network looking for the website. So if you're trying to go to www.cnn.com, that computer is actually going to look inside your little subnetwork to see if cnn.com is there. If it's not there, it will then use this default gateway. It will then go to the router and say, hey, I need to find cnn.com. That router will then go out to the internet, and through the whole bunch of magic of the internet, it will then find CNN.com, and it will create a link between CNN.com and your computer. So the default gateway is the router. If you're dealing with small networks, this will be the router, this will be the DSL modem, this will be the cable modem, this will be the ADTRAN, etc. Basically, the default gateway is what connects your subnetwork to all the other networks that are out there. You've been paying attention to what I've been saying. The Internet protocol, the IP protocol, connects computers based upon their IP address. So 10.1.10.1, let's say. And your computer only cares about an IP address. But you want to plug in something like CNN.com. This is where something called a DNS server comes into play. This is called a domain name server. What domain name servers do is they map domain names to IP addresses. So within this domain name server, it will say www.cnn.com equals, 201.65.33.2. So what's going to happen is you plug into your computer, into your web browser, www.cnn.com. Your computer doesn't care about this name. Can't really do much with it. But what it can do is it can take CNN.com, it goes and it talks to the DNS server. The DNS server then tells your computer that CNN.com is the IP address 201.65.33.2. Then looks at the internal network for the IP address. If it can't find it in the internal network, it then goes to your router, to your default gateway, and your default gateway then goes out to the internet and then connects your computer. Now the final component that you need to understand about for TCP/IP networks is something called DHCP. I think it's Dynamic Host Control Protocol. So every computer on the network needs to know its IP address, it needs to know its subnet mask, it needs to know its default gateway, and it needs to know what DNS servers to talk to. So there are two ways you can give this information to the computer. The first is by giving your computer what is called a static IP address. What this means is you sit down at your computer or the device and you plug in all the information manually. So you say this computer has an address of 192.168.1.55, has a subnet mask 255.255.255.0, has a default gateway of 192.168.1.1, and the DNS servers are 192.168.1.1 and 208.55.44.1. Now, as you can see, me simply writing this out on a whiteboard, and that took a couple seconds. You were probably getting a little bored while I was doing it. So what you can do is you can give the computers or devices on your network what are called dynamic IP addresses. And this is where DHCP comes in. So dynamic IP addresses mean that when the computer connects to the network, it will call out to the DHCP server. The DHCP server will then give it an IP address, it will tell it the subnet mask, it will tell it the default gateway, and it will tell it the DNS servers all automatically. And it will keep a record of the IP addresses that it has given out to make sure that it doesn't give out the same IP address to multiple computers. Your computer calls out to the DHCP server and it says, hey, I need an IP address. So you have configured in the DHCP server what the scope of IP addresses the DHCP server can give out. So you will tell the DHCP server, you can give out IP addresses 192.168.1.100 through 254. So this gives it a scope of 154 IP addresses that this DHCP server can give out. So this DHCP server will not give out 192.168.1.9. 99 because that is not within its scope. It will give out .1.105, etc. So the scope is the full range of IP addresses you allow the DHCP server to give out. You will then tell it what the subnet mask is. Again, we're going to go into this in a few minutes. And you would say 255.255.255.0, a class C subnet mask. You would tell it what default gateway you want it to give computers, so 192.168.1.1. This is the router, so how they're going to communicate with the outside world, and then what DNS servers that you want to tell the computers about, again, whatever that is. So your computer talks to the DHCP server and gets all this information. You have configured, or somebody has configured all this information in the DHCP server at some point in the past. Now, the DHCP server will then give all this information to your computer with something called a lease time. So what the lease time means is this is literally a lease on how long your computer is allowed to own that IP address. So your computer asks for an IP address. That IP address and all that information is given to your computer with a lease time. This lease time may be a day, this may be 7 days, it may be a month. It's all up to you as a system administrator. For DHCP, this is all dynamic. As soon as you plug your computer into the network, it will try to communicate with the DHCP server to get the IP address, the subnet mask, the default gateway, DNS, etc. The last thing that you should understand is something called network address translation. It's called NAT. You will hear about NAT a lot. So back in the days, 15 years ago, everybody was worried because they thought that every single computer device on the internet was going to require its own dedicated IP address. So that means your computer would require an IP address that was unique to the world, not unique to your office, unique to the world. Your printer, your network printer, would need an IP address that was unique to the world, etc. Because they thought every single device that was connected to the internet would need its own unique IP address. Well, then they came up with something called NAT, or network address translation, and this fixed a whole bunch of stuff. So you will see, this is our router, that most internal networks have IP address ranges in the 192.168.1.12.254. So, if you go to your little network inside your house, your computer inside your house may have an IP address of 192.168.1.2. You can go to your friend's house, and one of the computers inside his house also has an IP address of 192.168.1.2, etc., etc., etc. How this happens, or how this is able to work, is through network address translation. What happens is every router that connects to the internet, so whether this is a home router, whether this is a business router, whether this is an enterprise, whether you're dealing with IBM, every single router that connects to the internet needs its own dedicated IP address. So this building that Everyman IT is housed in, we have an IP address. Our computers, our servers that are sitting on the internet, they have individual IP addresses. My home router has an individual IP address. But then, once you get inside the router, you can use, or you can reuse IP addresses. So, like I say, all internal networks either use 192.168.1.whatever, or they use 10.1.10.whatever network addresses. All the internal networks. Because what happens is, let's say you have a computer here, it's 192.168.1.2, and you have 192.168.1.3 here. So this is your network. Then your neighbor has 192.168.2 also, and 192.168.3 also. Well, when you are trying to communicate to servers on the internet, the server that is on the internet is going to be most worried about what your external IP address is. So your external IP address will be, say, 208.55.44.1. So what network address translation allows is computer here, this 192.168.1.2, is going to go to your default gateway, and it's going to go out and it's going to find CNN.com. CNN.com is then going to say this communication came from this particular router. It will send the information back to this router. This router has NAT built into it, network address translation built into it, and it says, I know that internally the computer that was asking for this information is 192.168.2. And so it will then route the information to 192.168.2. Now, if this computer down here wants to go to, let's say, facebook.com, the external IP address for this router may be 209.77.66.44. So 192.168.3 is going to go to the default gateway to the router. That's going to go to the internet. That's going to go to Facebook. Facebook is going to go, oh, I see the person requesting this information is this external IP address. So Facebook will send the data back to this external IP address. NAT, network address translation, is built into this router. This router goes, oh, I see that 192.168.1.3 is the one that asked for this information, and then the information will get routed here. Well, basically, what those addresses signify is there are a number of values for what are called octets. So when you're dealing with TCP IP addresses, you're dealing with 4 octets. So octets are series of 8 numbers. So basically, you have 1, 2, 3, 4, 5, 6, 7, 8, dot. 1, 2, 3, 4, 5, 6, 7, 8, dot. 1, 2, 3, 4, 5, 6, 7, 8, dot. 1, 2, 3, 4, 5, 6, 7, 8. So when I say, let's say 10.1.10.1, the computer is actually looking at this big thing, which is a series of 4 octets to come up with this number. So 10 would be here, dot, 1 would be here, dot, 10 would be here, dot, 1 would be here. Now, when we're looking at this octet and where we come up with these numbers, so we'll look at a single octet. So 1, 2, 3, 4, 5, 6, 7, 8. So this is 8. These are 8 bits. So with this, they can either be 1 or 0, 0 or 1. So you can have 1, 1, 1, 0, 0, 1. It can be 1 or 0. So on or off. You can't have 2. 2 doesn't work. It's either 1 or it's 0. Now, how we get to the numbers then is starting on the right-hand side, we give each one of these spaces a number value. So here, this number value is 1. The second one in is 2, and it keeps doubling. So 1, 2, 4, 8, 16, 32, 64, 128. So these are the number values for these octets. So this is 1, 2, 4, 8, 16, 32, 64, 128. Then if you go to the next octet, you start over again. So 1, 2, 4, 6, or 8, etc. So each octet is entirely separate. So if you are trying to get, let's say, an IP address of 128. So 128, what you would do is you would put a 1 over the 128 and then a 0 over everything else. So this means count 128. So if I want, 192.168.1.128, you would just put 1 bit as true over 128. If, let's say you're trying to get 192.168.1.10, right? Well, then we look here and we say, okay, well, we've got an 8, so we'll make 8 true. And then we've got a 2, we'll make 2 true. And then everything else is 0. So if you want 192.168.1.10, that means 2 has a 1 over it, and 8 has a 1 over it. Does that kind of make a little sense? So, if you want, let's say, I don't know, address 254. So if you add all these up together, they will come out to be 255. So 255 if you add up all these together. So let's say you want an IP address of 254. So you'd say 1, 1, 1, 1, 1, 1, 1, 0. So 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2. That's it. And then you add all that up, and that will come out to 254. So this is what the numbers mean. This is how we get the numbers. This is going to be very, very important in a second once we start dealing with subnet masking. So basically, when you're dealing with an IP address or when you are dealing with a subnet mask, you are dealing with 4 separate octets. These octets are made up of 8 bits. The bits are either on or they're off, so 1 or 0. The way you come up with a number is, again, from right to left. You start with 1, then you double to 2, to 4, to 8, to 16, to 32, to 64, to 128. So all this will make a little bit more sense once we get into the subnet mask in a second, but this is the basic idea behind numbering and octets. So the IP address tells you the identifier for the network, and it tells you the identifier for the computer or networking device. Now, you're looking at this number and you're probably wondering, what part of this is for the network and what part of this is for the computer. Well, that is what the subnet mask tells you. So you will see something like 255.255.255.0. This subnet mask tells you what part of this IP address is the network identifier and what part of this IP address is the device identifier. Now, this is very, very important because devices on different networks cannot talk to each other. So if you have one computer plugged into a switch on network 1 and you have a printer plugged into the exact same switch, so they're physically on the switch. So you have a switch here, one goes to a computer, one, let's say, goes to a printer, right? The computer that is on the first subnet cannot talk to the printer if it's on another subnet or another network based upon the IP address, unless, of course, there is a router to connect them. So remember, routers connect different subnets. So if you have a computer on one network and a printer on a different network, they need a router to communicate, even if they're plugged in physically to the same switch. So this is very important to understand. So you can have multiple subnets, multiple networks, all plugged into the same physical switch. And this is not VLANs. This isn't like Cisco VLANs or like routing or switching VLANs. This is simply how TCP/IP works. So if you have computers on different subnets, on different networks, even though they're connected to a switch, so they're physically connected together, they still cannot talk to each other. So this is very important to understand. So the subnet mask is what tells you what part of the IP address is for the network and what part of the IP address is for the device on the network. So this here is what is called a Class C subnet. Since I know what's going on, I can automatically look at this Class C subnet and know that the network portion of this address is 192.168.1. So this is a 192.168.1.x network. And I can tell that the identifier for the device on the network is the 1. Now I can do that because I understand what subnet masking is. So now that we understand how all that works. Now, how you figure out a subnet is basically you decide. So we talked about the numbering system before. So we have 4 octets of bits. A bit can either be a 1 or a 0, remember? And depending on how the 1s and 0s are up here, you get a different number. So like this 1 right here, in order to get 192.168.1.1, that means we have 0, 0, 0, 0, 0, 0, 0, 1. And that makes 1. If we wanted, let's say 3, it would be 1, 1, 0, 0, 0, 0, 0. So remember how we talked about the numbering system before. So what we do is, using these octets, we decide how many networks we need in our network, in our overall network, and how many hosts we need in our overall network. And then all we do is we use that many bits
that we need to accomplish our task. So we just divide it off anywhere in here. So we can say right here, we want everything to this side to be the network number, and everything to this side to be the device number. Or we can come here, and we can put it here. Or here, or here. It doesn't matter. We can decide depending upon the subnet mask. So when you're trying to figure this out, the thing to think about is it depends on how many networks you're trying to create or how many devices you're trying to shove into a single network. So depending on how many bits you use for your network, there is an equation, and for the networks, it is 2n. So the total number of subnets you can have is 2 to the power of however many bits you have used for the subnet. So let's say you want to use the first 8 bits out of the 4 octets for a subnet. So it would be 2 to the 8th. And that will tell you how many subnets you can have on this network. Now, if we're trying to find hosts, so this way is for networks, this way is for hosts, you have 2 to the n minus 2. So let's say we wanted 254 hosts. That's a standard. That is using 8 bits from this first octet. So this is a class C subnet. So it would be 2 to the 8th minus 2, and I just know this by heart, which comes out to 254 hosts. So what you're doing when you're creating the subnet is you have to figure out either how many networks you want or how many hosts you want. And then, depending, you basically count one way or the other. If you need lots of networks, then you count out how many bits you need from left to right, and then you just take those bits for your subnet network. And to figure out how many subnets you can have here, it is 2 to the n. 2 to the exponent of however many bits you have taken. If you're trying to figure out how many hosts you need, you go right to left, and then you just take the bits as you need. And so 1, 2, 3, 4, 5, 6, 7, and you keep going, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, however many you need. So if you need, let's say 508 hosts on a, or no, it would be more than that. But basically, you just go across, and that way it is 2 to the n. So the n is how many bits you use, 1 or 2 or 3, minus 2 tells you how many hosts. So that's all you have to do to figure out the subnet, how many subnets or devices you need. Now, when you're dealing with this, all you do then to figure out the subnet mask is, again, 1, 2, 3, 4, 5, 6, 7, 8, dot, 1, 2, 3, 4, 5, 6, 7, 8, dot, 1, 2, 3, 4, 5, 6, 7, 8, dot, 1, 2, 3, 4, 5, 6, 7, 8. So these are the 4 octets. To figure out the subnet mask, you just add up all of the bits and then the number. So remember, when we're dealing with an octet, 1, 2, 3, 4, 5, 6, 7, 8, remember the number positions. This is 1, this is 2, this is 4, this is 8, this is 16, this is 32, this is 64, and this is 128, right? So if we're trying to figure out a subnet, and let's say we decide to use all of the first octet for the network, for the subnet networks. So if we add up 1 and 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 1, if we add up all these, right, then that comes to 255. And then we do dot, because that's the octet, and then there's nothing here, and nothing here. So that would be 255.0.0.0. So the subnet mask, if you were doing this, would be 255.0.0.0. Now, let's say we wanted to do 111, 111, 111. So we want to use all of that, right? So then that would be 255.255.0.0. And if we wanted to use all of that, 1, then it would be 255.255.255.0. So now you may have seen these particular subnets before. 255.0.0.0, 255.255.0.0.0, and 255.255.255.0. These are the classic A, B, and C subnets. So an A-class subnet is 255.0.0.0. A B-class subnet is 255.255.0.0. A Class C subnet is 255.255.255.0. So if you ever hear about this, when you have normal networking people all talking back and forth and they say, it's a Class C subnet, what they mean is that the subnet mask is 255.255.255.0. If they say it's a Class A subnet, it's 255.0.0.0. So you follow me there? Now, okay, so you've seen these standard ones, 255.0.0.0, 255.255.255.0. Well, sometimes, since you are going to be a really cool network engineer, you are not going to divide your subnets on the octet, right? So 1 octet, 2 octets, 3 octets, 4 octets. Sometimes you're just going to have to be crafty, clever, cool, and not use the 255 subnets. So let's say you were given a whole Class C subnet. So you are in an office, and your higher level network person gave you 254 hosts. So they gave you a Class C subnet, 192. Let's say .168.1.x, and that's 255.255.255.0. So you're allowed to use this. But you want to divide this into 2 networks, right? Well, so we're using all the ones here, all the bits here, all the here. So let's say we just want to create an extra couple of networks. So we're going to steal a couple of bits out of this Class C subnet. So with this, all you do is, of course, because we use all the numbers here, that's 255, period. We use all the numbers here, 255, period. We use all the numbers here, 255, period. But here, we only want to use 2 bits. So then we do 1 here and 1 here, right? Because that's where the division for the subnet will be. We add that up, and then this subnet mask will be 255.255.255.192. So now we can use these 2 bits to create different networks. So that's how that works. The important thing to realize, though, is how to count how many different devices you can have on any particular subnet, because this will be important, especially in larger environments. Because, like I say, if you have a Class C subnet, so Class C is 255.255.255.0, that means you're using 8 bits for the device identifier, which means you have 2 to the 8th minus 2, which comes out to you can only have 254 devices on this network. You try to plug in 300 devices, especially if you have something like a DHCP server, it's all going to get nasty really quick.